Hey everyone, and welcome to This Explainer. Okay, so today we're diving into something absolutely fascinating. We're going to decode exactly how AI sees and identifies objects and images. If you've ever wondered how a self-driving car manages to spot a pedestrian in literal milliseconds, or say how your phone automatically groups all those photos of your cat together, well, it all comes down to the magic of object detection. Specifically, we're going to look at a legendary, totally groundbreaking model called YOLO v1. And hey, don't worry, we're doing this without getting instantly lost in a sea of intimidating math. We'll take it step by step so we can all get a really solid grasp on how this actually works.
So, here's our roadmap for today. We'll kick things off with defining object detection, then move right into the grid system, take a look at boxes and labels, dig a little deeper into the mathematical core, and finally, we'll review the final predicted map.
All right, Section 1. What is object detection? Let's lay down the foundation.
To start, we really need to detail the exact inputs and outputs, because this is basically the bedrock of the entire concept. Our input is super straightforward, right? It's just a single static image. But the output, well, that's where the real challenge lies. We actually need two distinct things from that one simple image. First, we need a set of bounding boxes, which are represented here mathematically as B1, B2, all the way to Bn, just standing for n number of detected objects. And second, we need class labels, C1, C2, straight through to Cn, for all of those detected objects. So think about it. We need precise boxes to map the geometry, and precise labels to determine the identity, all at the exact same time.
And this image right here brilliantly illustrates that final output goal. We've got C1 representing our person class, and C2 representing our horse class. Now, the computer isn't just giving us a vague, fuzzy idea that, oh, there's a person and a horse somewhere in this general area. No way. It's explicitly assigning that specific C1 label to the exact pixels containing the person, and the C2 label to the pixels containing the horse. It is definitively tying the semantic identity straight to the visual data.
Moving on to Section 2, the grid system. This is all about dividing and conquering.
Now, I want you to notice how the system handles the visual space here. You can see our base 448 by 448 pixel image of the person and the horse, but look at what is overlaying it. The image is chopped up into this really distinct purple grid. This is huge. Instead of an old-school approach where an algorithm might just painstakingly scan the image over and over again in tiny little patches looking for shapes, YOLO basically says, let's divide the whole thing into this grid structure right off the bat. This lets the algorithm analyze the horse and the woman simultaneously in one single pass. It literally turns a massive, messy searching problem into a highly organized, localized prediction problem.
All right, Section 3, boxes and labels. Let's see how it actually draws the lines. By comparing the macro view of the entire grid on the left with this zoomed-in view of the legs on the right, we can see exactly how the computer calculates these box dimensions. If you look closely at the mathematical annotations on the right side, you'll see the system calculates the width and height of the bounding boxes, like H1 and W2, by using a fraction of the total 448-pixel height and width. It takes the precise geometric boundaries of the objects and anchors them right to the exact dimensions of that original 448 by 448 visual grid. That is how it knows exactly where an object starts and where it ends. So taking those raw pixel calculations we just saw, the system steps through a really logical, highly structured sequence. Step 1, it analyzes those grid boundaries we overlaid on the image. Step 2, it calculates the specific bounding box dimensions relative to that grid space. And finally, Step 3, it applies the final label encoding. Basically, this just means that the sides of the box it just drew actually contains a person, a horse, or, just some background dust.
Okay, Section 4. Let's dig deeper. Time to look at the mathematical core.
Now, before we look at the final output, we do need to peel back the layers of the complex loss computations. These are what actually train this network to get smarter and more accurate over time. Take a deep breath. It's going to be fine.
We're going to start small by defining the foundational summation component. This specific piece of the puzzle is responsible for calculating loss across all grid cells. Now, if you're not super familiar in machine learning, loss is essentially just the measure of how wrong the computer's guess was. The higher the loss, the worse the guess. So this summation component simply means the algorithm is systematically scanning across the entire grid to check its accuracy. And here is exactly what that looks like in the formula. You can see the mathematical summation symbol there, iterating from I equals 1 all the way up to s squared. And that s squared, that just represents our total number of grid cells, our purple grid from earlier. So mathematically speaking, this is just the computer methodically looping through every single square to see what's going on inside of it.
Next, we add this piece right here, the object I variable. This acts as an absolutely crucial check for our system. It asks a really simple binary question. Does an object actually exist inside that specific grid cell I? If there's no object in that grid space, well, the system doesn't need to stress over the bounding box math for an empty patch of dirt, right? It acts as a powerful, hyper-efficient filter for our loss computation.
So the real takeaway here is that this massive, kind of intimidating loss equation you see mapped out is really just combining everything we've talked about so far. It brings together our 448 by 448 grid, our boundary calculations for the boxes, and our label encodings, and it uses all of them together to train the network step by step. It calculates the geometric errors in the box coordinates, the errors in its confidence that an object is even there to begin with, and the errors in the class probabilities. It sums it all up so the neural network knows exactly how to adjust its weights and improve its vision for the very next image.
Finally, Section 5, the final predicted map. Let's put it all together.
Let's walk through this entire pipeline, end to end. We start on the left with our raw image of the person and the horse. That image is fed directly into the YOLO v1 convolutional network, and instead of piecing things together slowly over multiple agonizing stages, it outputs a dense, three-dimensional predicted map measuring 7 by 7 by 30 in one single shot. That final 3D block you see on the right contains all the spatial grid data, all the bounding box confidence scores, and all the class predictions computed at exactly the same time. It's truly a thing of beauty.
We've seen how YOLO looks at an image exactly once to figure out what's there and exactly where it is. So I'm going to leave you with this final provocative thought. If YOLO v1 can instantly map a static grid and calculate all those boxes and labels in a fraction of a second, how might this single-pass approach revolutionize the way computers process live moving video? Just imagine the real-world impact of lightning-fast, grid-based object detection constantly updating on a camera driving down a busy, chaotic highway, and completely changes the game. Thank you so much for joining me on this explainer. I hope you really enjoyed breaking this down with me, and I'll catch you next time.